Fet Input Voltmeter. Why we are going for electronic voltmeters? So it is for low level signal detection. Mainly we are going to select electronic voltmeters are it avoids the loading effect, the power consumed is low, and the voltmeter electronic voltmeter can be used for a high frequency range of operation. Here, if the signal levels are low, then mechanical deflection types of instruments produce a loading effect. That means the instrument will consume an appreciable amount of power and there is a chance that signal may be lost. But electronic instruments are capable of providing power so that we can measure a voltage in terms of microvolts also. The power consumed by these instruments are low as they can provide very high input impedance up to a few hundred megaohms. So, the current in the circuit is much small and hence the power loss is reduced. In the electronic voltmeter, the measurement is almost independent of the frequency of operation. They have a very high range of operating frequencies up to few megahertz. The frequency response is much wider as the capacitance of the input circuit is very small. Here you can see the circuit of a FET input voltmeter. In this voltmeter, FET is used in the input stage because of its high input impedance so that it does not load the circuit in which the voltage is to be measured. Next, also it keeps the sensitivity of voltmeter very high. In this voltmeter, the voltage to be measured is firstly attenuated with a range selector switch to keep the input voltage of the amplifier within its level or within its limits. As FET is a voltage control device, so a resistance network of attenuator is put in shunt in the circuit. The transistor is used as a direct coupled amplifier whose output is finally supplied to the PMMC meter. When the transistors work within their dynamic region, the deflection of the meter remains proportional to the applied input voltage. Apart from the high input impedance, this circuit has another advantage that when by chance input voltage exceeds its limit, the amplifier gets saturated, which limits the current passing through the PMMC meter so that the meter does not burn out, does not get damaged. This type of voltmeter is very common because of its low cost, and also this instrument can be used only to measure voltages of the order of millivolts owing to limited amplifier gain. In the attenuator section, the range selecting resistors are so chosen that the sensitivity remains the same for all ranges. So, the current drawn from the circuit is very small, 5 microamps. The disadvantages of this voltmeter is that it has to work under specified ambient temperature to get the required accuracy. accuracy. Otherwise, there is the excessive drift problem during the operation. One more thing is the cost may be high as we are using more electronic components. And one more disadvantage is that if any one component gets damaged, the whole circuit has to be replaced. Now, let us see the construction and working of this Fet Input Voltmeter. The circuit has three sections: the range attenuator section, the source follower section, and the bridge circuit. Here, the source follower drives an emitter follower. The source follower circuit is able to provide high input impedance and low output impedance and is used to act as a buffer amplifier. The low input voltages need to be amplified at measurable levels, and electronic circuits are required to offer high input resistance. So a BJT emitter follower is used where PMMC and resistor are connected to its emitter. This combination is capable of 1,000-fold or more increase in the input impedance while maintaining a voltage gain of nearly 1. So the input impedance of this voltmeter is of 1 mega ohms, which would require 0.025 microwatts of power for a 0.5 volts deflection as compared to 25 microwatts for an unamplified meter, and the sensitivity is increased 100 times. Here, as I told you, we have the attenuator section, the FET for source follower section, and the bridge circuit. The ranging attenuator section is nothing but a potential divider circuit with 3 resistors connected in series, and this section is used to select the different ranges, voltage ranges 500 millivolts, 5 volts and 50 volts range. Here we have a single pole 3-way rotary switch which is used to select the required range of voltage. The rotary switch is connected to the gate of FET by 1 mega ohm resistor which is used to limit the gate current so that the FET will not be damaged. Next, the FET is connected in source follower configuration and the transistor Q2 acts as its load. The transistor emitter resistance is 10K, the 2.5 kilo ohms potentiometer and 2.2K resistor acts, these four together act as 4 arms of the bridge circuit. The switch S is to apply the power supply to the circuit. As we have seen, a 10 kilo ohms calibration potentiometer and a micrometer are connected to the circuit by means of a switch S. Now, coming to the working of the FET voltmeter, as I told, the FET is connected in source follower configuration for obtaining the impedance matching, thus delivering the maximum power to the load and thereby providing high accuracy. If you speak about the working of the FET input voltmeter, it can be divided in 3 parts. One is for zero adjustment, one is for calibration, the last one is the actual measurement of the input voltage. So, for zero adjustment, when switch S is closed for power supply to the circuit and the test terminals T1 and T2 are shorted, the two test terminals are short circuited, there is no drain current in the FET. Thus, there is no emitter current following in the transistor. Therefore, the microammeter which is connected between the points of the bridge should show zero reading. If it's not showing zero reading, then there is a zero adjustment potentiometer, that is the 2.5 kilo ohms, which you can adjust slowly so that the meter shows the zero reading. Next is the calibration section. Now the short circuit between the two terminals is removed and a small voltage of 500 millivolts is connected across the test terminals T1 and T2. The 500 millivolts voltage range is selected by means of the rotary switch, that is the range switch. Now, the known voltage source causes current to flow in the drain of the FET. This causes an emitter current to flow in the transistor. This results in a voltage drop across the emitter resistance RE. This causes a deflection in the microammeter. The 10K calibration potentiometer is adjusted until the meter shows the full scale deflection, that is the 500 millivolts. Now the meter is ready for the actual measurement. Actual measurement is nothing but now apply the unknown voltages between the two test terminals T1 and T2. The microammeter then deflects in proportional to the unknown voltage. So, if the rotary switch is in 500 millivolts range, then the reading can be had directly. If it is in 5 volts range, the reading should be multiplied by 10, and if it is in 50 volts range, the reading should be multiplied by 100. So, this is the construction and the working of a FET voltmeter. So, if I want to measure the AC voltages using this FET input voltmeter, the AC voltages can be converted into DC voltages with the help of a rectifier. The rectified DC voltage is applied at the input terminals of the FET input voltmeter. So, this is the simple block diagram of the AC type of FET input voltmeter. So, these are the working principles and the advantages and the disadvantages of a FET voltmeter. As we have already seen, the advantages of the FET voltmeter is there is no loading effect, hence the power consumed by this instrument is very low, and the operating range of the voltmeter is high up to megahertz, and the sensitivity is uniform for all the ranges and it remains same. When you come to the disadvantages, as we have already discussed, there is excessive drift problem, this FET input voltmeter, because it has to be used in the same specified ambient temperature. The other disadvantage is we are using the electronic components, the cost may be high, and if by chance any component gets damaged, the whole circuit must be replaced. So this is about the FET input voltmeter. Thank you. Differential voltmeter. A differential voltmeter works on the principle of comparison of unknown voltage with known voltage. This is one of the most common and accurate methods of measuring unknown voltages. In this technique, the voltmeter is used to indicate the difference between a known voltage and an unknown voltage. That is, an unknown voltage is compared to a known voltage. The basic differential amplifier, a basic differential voltmeter is as shown in this figure. It uses a null indicator which is connected between the known voltage and the unknown voltage through a potentiometer. Here, in this differential voltmeter, the principle of working is similar to the potentiometer and hence it is known as potentiometric voltmeter. In this method, the potentiometer is varied until the voltage across it equals the unknown voltage. The equality of this known voltage and unknown voltage is indicated by a null detector. The null indicator indicates 0 when the two voltages are same. Under null condition, the meter draws current from neither the reference source nor the unknown voltage source. Hence, the differential voltmeter presents an infinite impedance to the unknown source. This is an AC differential voltmeter with little modification. A DC differential voltmeter can be used as a AC voltmeter. Here in the block diagram, you see an unknown AC voltage to be measured is applied to the input of the attenuator. It is used to select the range. This voltage through the attenuator consisting of number of resistors for different ranges is used in the voltage divider mode. The attenuator output is given to the AC amplifier which amplifies the small signals. This amplified AC voltage is then converted to DC voltage by using a precision rectifier circuit. Once the DC output voltage is generated, that it is proportional to the AC input voltage, then as already explained, that is compared with a known reference voltage, and the known reference voltage potentiometer is slowly varied until the null indication meter shows as 0, which means that the unknown voltage now is equal to the known reference voltage. In this way, the unknown AC signal voltage can be measured. A differential voltmeter. A differential voltmeter is one which can be operated in three different modes. The DC voltage standard mode, the DC differential voltmeter, the last one as I said DC conventional voltmeter. In the DC standard mode, this differential voltmeter is as shown in the figure. Here, a 1 volt DC stable supply is obtained from a temperature controlled reference supply, which is applied to a decimal divider network with the help of switches on the front panel of the voltmeter. The divider ratios can be varied, allowing reference supply to be adjusted in steps of 1 microvolt each from 0 to 1 volt. A low-level DC amplifier is used to amplify the low-level voltages obtained from the decimal divider to a sufficient level. This reference output voltage is then applied to a high-gain DC amplifier. In the standard mode of operation, the differential voltmeter is used to provide a standard reference source in the laboratory. This instrument generates DC voltages from 0 to 1000 volts. There are different ranges in which the meter generates. The standard voltages are available in the different ranges as 0 to 1 volt, 0 to 10 volts, 0 to 100 volts and 0 to 1000 volts. Next, one of the modes is the standard mode. The next mode is the differential voltmeter mode. In this differential voltmeter mode, the unknown DC voltage is applied to the input of the amplifier section, and a part of the output voltage is fed back to the input stage with the help of one of the divider networks, which controls the closed loop gain of the amplifier. The other section of the voltage divider network applies a fraction of the output voltage to the differential input of the meter amplifier. The meter circuit here measures the difference between the feedback voltage and the reference voltage, indicating a null deflection when two voltages are equal. So this is the differential voltmeter mode of the differential voltmeter. And the next one is the conventional DC voltmeter. In this mode of operation, it is connected as a DC voltmeter. The high input impedance to the unknown voltage source is provided by DC amplifier, which acts as a buffer. The input voltage is amplified and the DC output voltage is applied directly to the meter circuit. As already explained, it works as an ordinary differential potentiometric voltmeter, wherein the unknown voltage is compared with the standard known reference voltage, and when both are equal, then it is indicated by a null indicator. So the unknown voltage is nothing but equal to the known reference voltage. So this is about the differential voltmeter, its principle of working, what it is basically, and next the practical circuit in which we are using it as the standard reference voltage, next as the differential voltmeter, and the last one is a conventional DC voltmeter. Thank you. Drift problem in FET voltmeter. The main drawback of a FET voltmeter is that it has to work under specified ambient temperature to get the required accuracy, or else excessive drift problem occurs during operation. The drift in ordinary instrument is of the order of millivolts. Hence, the range is limited to few hundred millivolts only. But In a chopper amplifier, as the drift is very small, the voltages in microvolts can be measured with good accuracy limits. The drift is the gradual shift of the instrument indication over an extended period during which the value of the input variable does not change. So the drift is undesirable because the readings are not precise and they may change. There are many environmental factors which affect the drift. These factors are the stray electric field, the stray magnetic field, the temperature changes, the contamination of the metal, etc. So, an instrument is said to have zero drift if it reproduces the same readings at different times for the same variation in the measured variable. The zero drift is defined as the deviation in the instrument output with time from its zero value when the variable to be measured is constant. The whole instrument calibration may gradually shift by the same amount. So the drift problem can be overcome by employing a chopper amplifier in which the drift problem which exists in the Fet voltmeter is overcome. Thank you. A chopper type DC amplifier voltmeter is one in which the DC input voltage is converted into an AC voltage. It is amplified by an AC amplifier and then converted back into a DC voltage proportional to the original input signal. The balanced bridge voltmeter has limitations caused by drift problems in DC amplifier. Any fluctuations of voltage supply or variation in the Q characteristics due to aging or rising temperature causes a change in the zero setting or the balance. This drift in the steady state conditions of a DC amplifier causes the output indications to change as if the signal input had changed. The drift problem limits the minimum voltage that can be measured. To measure small voltages, a chopper type DC amplifier is used. A chopper amplifier is normally used for the first stage of amplification in very sensitive meters of a few microvolts range. In such an amplifier, the DC voltage is chopped to a low frequency of 100 to 300 Hz. It is passed through a blocking capacitor, amplified, and then passed through another blocking capacitor in order to remove the DC drift or offset of the signal of the amplified signal. And this is how in a chopper amplifier the drift problem which was in the Fet voltmeter is overcome. In this chopper amplifier type voltmeter, an AC amplifier which has a very small drift compared to a DC amplifier is used. The chopper may be mechanical or electronic. Photodiodes are used as non-mechanical choppers for modulation, that is, the conversion of DC to AC and demodulation, conversion of AC to DC. The photoconductors have a low resistance ranging from a few hundreds to few thousand ohms when they are illuminated by neon or incandescent lamp. The photoconductor resistance increases sharply, usually to several mega ohms when not illuminated. So, a flashing light source whose intensity varies from maximum to minimum almost instantaneously to change from arming to armor quickly is used. Therefore, the output voltage is an AC because the photodiode has a high output when its resistance is high and a low output when the resistance is low. So, these are the components which we use in the chopper section to obtain the chopper type voltmeter. The chopper eliminates the need for a high gain DC amplifier with its inherent drift and stability problems. The input impedance of a chopper amplifier DC voltmeter is usually of the order of 10 mega ohms or higher except in low input ranges. So, in order to eliminate the errors caused by high source impedance, an arrangement for nulling is included in the meter circuit. A control facility is provided on the front panel of the instrument which permits the input voltage to be nullified with the bucking voltage. So the input voltage, when the bucking voltage is equal to the input voltage, the null is indicated, the meter exhibits infinite impedance and therefore the loading effects are totally eliminated. The input voltage is then removed and the bucking voltage equal to the input voltage is indicated by the meter. Commercially available instrument using a photochopper amplifier has an input impedance of 100 mega ohms, a resolution of 1.1 microvolts. The input range from 1 microvolts full scale to 1 kilovolts full scale with an accuracy of plus or minus 2% of full scale deflection. So, the advantages of a chopper amplifier is the input impedance is very high of 10 mega ohms and the drift in an ordinary DC amplifier is of the order of millivolts. The full scale range of an ordinary DC amplifier is 1 to 100 millivolts. In a chopper modulator system with the use of AC amplifier, drift can be cut down by a factor of 100, thus allowing an input signal range of about 0.01 millivolts, that is 10 microvolts full scale to be handled. In this way, the drift problem is avoided in a chopper amplifier. Chopper amplifier type DC voltmeter. Thank you.